Continuation with lectures on organic synthesis. Today the topic of discussion will be one group carbon X bond disconnection. The key concepts of today's lectures will be retrosynthesis. So we will discuss briefly about basic concepts of retrosynthesis, the functional group interconversion, basic rules for retrosynthesis, disconnection approaches for different classes of organic compounds, and some practice problems. A review on the retrosynthesis analysis. So the retrosynthetic analysis approach involves breaking an organic compound into fragments through a series of logical disconnections to get best possible starting material. So the retrosynthesis just means that when you see a compound, an organic compound, and by just seeing that, you can just imagine that if you break this bond can be formed by reacting this X reactant with this Y reactant to form the product. So retrosynthesis is just logical disconnection. We are not actually breaking a bond in an organic compound. We're just doing the logical work on paper. So since the retrosynthetic analysis approach involves breaking of bonds between atoms, so that's why this approach is also called disconnection approach. And since it's actual reverse of synthesis, this is also called retrosynthesis. Right? The purpose of retrosynthesis is to reach suitable starting material before carrying out the actual synthesis. So first we should know about certain terminologies such as disconnection. So disconnection is an operation that involves breaking of bond between two atoms. Again, for your reminder, it means breaking the bonds on just paper. Right? So we are imagining that we are disconnecting the bonds between atoms of a product to reach a suitable reactant. Second important term that's used in the retrosynthesis is the synthone. Synthone is an idealized fragment, usually an ion or radical, obtained by disconnection. So when we break the bond between atoms in a product, the fragments that are produced are called the synthone. Reagent is the actual chemical that will be used to carry out synthesis. For example, a synthone may be a methyl radical or methyl cation, and the reagent that will provide the methyl cation will be methyl sulfate, for example. Okay, the next term that's used in retrosynthesis is the FGI or FGE. So FGI stands for functional group interconversion, and FG stands for functional group equivalence. So both means the same. So whenever you carry out retrosynthesis, this arrow is used. So whenever this arrow you see, it means this is retrosynthesis. The interconversion of one functional group to another is called functional group interconversion or functional group equivalence. So if you convert an alcohol into a carboxylic acid or an aldehyde, so we are not breaking any bond, right? So we're just converting an alcoholic group into carboxylic group. However, if we are substituting a halogen with an OH, so we have broken the bond between carbon and Cl and have substituted with carbon OH bond. So this is not functional group interconversion. Interconversion means that the functional group remains intact and we're just converting it into one form or another. So if we convert alcohol into aldehyde, this is functional group interconversion. But if you replace Cl with OH, this is called disconnection approach. This is not functional group interconversion. Okay. So the most important rule in disconnecting a bond is that disconnection must result in formation of a stable fragment. So synthones must be stable. For example, if you break a bond, right, so you form a carbon with a positive charge and a carbon with a negative charge. So you should ensure that carbon with negative charge is stabilized and the carbon with positive charge is also stabilized. So for example, in the compound given below, we have two possible disconnections possible. So one is A disconnection. So in A disconnection, we have a negative charge on carbon, and this carbon is attached with nitro group, and a positive charge on carbon, and this carbon is attached with an R group. And in the B disconnection, we are having carbon, which is positively charged, attached to a nitro group, and carbon, which is negative charge, is attached within R group. So in the A disconnection, the negative charge is stabilized with the nitro group. So nitro group can attract the negative charge. So negative charge is stabilized by nitro group, while the R group, because of hyperconjugation, can stabilize this positive charge. So both syntones that are obtained in the A disconnection are stabilized. But in case of the B disconnection, the carbon, which is positively charged, is deficient, and nitro is also creating a deficiency. So nitro is not stabilizing this positive charge, instead it is destabilizing, so this syntone is unstable. Similarly, the carbon with negative charge is attached to an R group. So R group is also electron donating, and carbon is also electronically rich. So this negatively charged anion will also unstable. So since B disconnection leads to formation of unstable fragments, the B disconnection will not be favored. So here the disconnection that is more suitable will be the A disconnection. The second important rule in retrosynthesis is that number of fragments generated must be minimum. Alright, so again we have two same products and we are considering how to make this. So again, retrosynthesis, so we go for retrosynthesis. So we break the bond between carbonyl and the CH2. So we get two fragments. So here we have positively charged fragment and we have a CH2 here. And okay, so in the A approach we see that this positively charged synthone can be generated from an ester, right? And so this other fragment, we have a halogen here, right? So we say the halogen can be brought back by substitution within hydroxy group, and this hydroxy group can be generated by considering an epoxide and reaction of this epoxide with a ketone. So, and this ester can be converted from, suppose, a ketone itself, right? So suppose this is our disconnection for A approach, while the B approach, we simply think that we have a synthone A, right? And synthone A can be thought from a ketone, and we have synthone B, and synthone B can be considered to be obtained by conjugate addition to a conjugated system, right? So this is alpha beta enone. So in the synthone B, in the disconnection B, since we have only two fragments obtained, and in case of disconnection A we have a large number of synthones, so disconnection B will be approached, will be favored, will be preferred, because it is involving formation or generation of least number. Okay, the next important thing you should know in retrosynthesis is that positively charged and negatively charged fragments generated as a result of disconnection are replaced by recognizable and meaningful chemical entities, right? So simply, if you want to convert a positively charged fragment into a useful entity, simple way is that to attach something that's a negatively charged atom or electronegative atom to the positive charge. So positive charge means deficiency, and deficiency is caused by something that is making it deficient. So always a deficient carbon is attached with an electronegative atom, such as a halogen, an OH group, a ether functionality, etc. So if you have to convert a positive charge fragment into useful, meaningful entity, simple way is that to attach an electronegative atom to that positive charge. And if you have a negative charge, simple way is to attach a proton, right? So when a base picks a proton, so you get a negative charge. This is simple. So whenever you have a negative charge fragment, the easiest way to convert it into meaningful entity is to add a proton to it. And when you have a positive charge, the simplest way to convert it into a meaningful entity is by attaching an electronegative atom such as halogen. Right. So coming to the point, whenever there is a carbon X disconnection, so X can be an hetero atom, It can be an oxygen, sulfur, nitrogen. So whenever a carbon X bond is broken, the heteroatom must bear the lone pair, the negative charge, while carbon must be positively charged. So this is the rule. Whenever you break a bond between carbon and X, the X always should bear either the lone pair or the negative charge. Carbon should not bear the negative charge. Right, so in CX disconnection, we disconnect a bond. Whenever you disconnect a bond, that should always be between a carbon and a halogen, right? So disconnection is the fundamental design. So all disconnections are one group disconnection. You have to just disconnect one bond. So we have, whenever we carry out a CX disconnection, we have electron deficient species, which is electrophile, that's positively charged, and the other is always electron rich species, that means that should be the nucleophile. So in this specific disconnection between R and X, whenever we disconnect the bond, so X, that's the heteroatom, should always bear the negative charge, and R should be the positively charged fragment. So when you are to convert these fragments into meaningful entity, its positive charge should be attached with some electronegative atom. So here we have attached a halogen, and X, that's a negatively charged, should be attached by a proton. So here we have attached proton. So we have converted the synthones into meaningful entity. This is the basic design for CS disconnection. Okay, so we have some practical examples. So go for it. For example, we have this compound. So the commercial name for this compound is chlorobenzyl. Okay, so firstly we have to disconnect the bond between carbon and sulfur. So here the disconnection will be this one. So never try to break a bond between an aromatic ring and a sulfide or any heteroatom. Okay, always go for the disconnection between sulfur and the aliphatic carbon. Don't go for the disconnection between sulfur and the benzene. So benzene with positive charge is never stable. So we have to generate a fragment that is stable. So benzene with a positive charge is not stable. That cannot be stabilized, right? So here we have the disconnection between sulfur and carbon. So again, by the rule, sulfur being heteroatom should bear the negative charge. So here we have negative charge on sulfur and the carbon is positively charged. So next we have to convert them into useful fragments. So sulfur, which is negatively charged, should be attached with the proton. So here we have a thiol group, and the positively charged should be attached with any electronegative atom. So here we have attaching chlorine. So if you have to carry out the synthesis, these are your reactants. So always remember, the last step of the retrosynthesis is the first step of synthesis. So these are your first reactants. So by reacting thiol with this benzyl chloride, you will get the product. So this is the synthesis. So reaction can be carried out by making use of sodium ethoxide as a base in presence of ethanol. So this base will pick up the proton from the SH, the thiol, converting it into negatively charged fragment. This negatively charged fragment will attack on this carbon, which is deficient because of attachment of chlorine. The chlorine will be displaced and we get a carbon sulfur bond. Okay, so we are going to discuss now different synthetic approaches, disconnection approaches for different functional groups, one by one for ease. Okay, so here we are going to discuss about the disconnections for alcohol, ether, alkyl halide, and sulfides. Right, so one thing is important that we have discussed. Whenever we disconnect a bond between carbon and X in any aliphatic compound, we get a nucleophile, that's XH, and an electrophilic carbon species. So usually represented by alkyl halide, the carbon that's electronically deficient, positively charged, is normally represented by an alkyl halide, or alternately we can make use of tosylate or methylate. And these alkyl halide, tosylate, or methylate can be easily obtained from alcohol. For example, you can see the interconversions. So by reacting an alcohol with phosphorus tribromide or HBr, we can convert alcohol into alkyl halide. By simply reacting alcohol with tosyl chloride, we can form two sulfides, and by converting or reacting alcohols with methyl chloride in presence of triethylamine, we can form the methylate. So both of these meaningful entities are alkyl halide tosylate or methylate, they can be easily obtained from alcohols. Therefore, alcohols are central to the CX bond. So here you can see how we can interconvert alcohols into different functional groups. This is a functional group interconversion. So alcohols can be interconverted into alkyl halide. Right, so alkyl halides upon alcohol reaction with alcohols in presence of base can form ether. Alkyl halides upon reaction with thiols can form thioether. Alkyl halides upon reaction with thiourea or okay, so there's a problem in this. So we have used a SH negatively charged, so this is not OH negative, this is SH negative in presence of water. So you can form thiols from alcohols, from alkyl halide, or we can displace this OH, right? So in case if the X is tosylate, upon reaction with the halogen, you can convert it into alkyl halide, and by making use of any nucleophile, you can bring any nucleophile in place of this X. The X can be halide, it can be tosylate, or it can be methylate. Okay. So in case of synthesis of this ether, we have made use of an example called gardenia. So gardenia is an ether, and here we are to carry out the disconnection for this ether, right? So there are two possible approaches. We have to make the carbon and oxygen disconnection. So there are two possibilities. Number one, we can break the bond between oxygen and A carbon, or we can break the bond between oxygen and B carbon. So consider that we carry out the A disconnection, right? So in that case, the oxygen should be the negatively charged and the carbon should be positively charged. So here we have A carbon with a positive charge and the B carbon with a negative charge, right? So in order to convert these into useful fragments, we have to attach a halogen with positively charged carbon. So we have benzyl chloride here as 5, and we have attached proton to 6 carbon, so we have an alcohol here, right? So we know they are meaningful reactants, both can be used. So consider the next fragment, right? So in case of disconnection B, we can disconnect here, so we will get oxygen with negatively charged, so we will get benzyl alcohol upon attaching a proton to this alcohol alkoxide, and by attaching a halogen to this carbon, we can get an alkyl halide. So we have two possible reactants, 5 and 6 or 7 and 8. So we see that which of these can be useful. Right, so since it doesn't matter which side is disconnected, both will yield an alcohol and alkyl halide. Both can be used for synthesis, or for practical reasons. What we prefer that we make use of benzyl chloride. So number one, is readily available. Second, there is no possibility of elimination in the benzyl chloride fragment. So by generating alkoxide out of alcohol, the reaction of alcohol with benzyl chloride will lead to formation of desired product. So one thing is important, that either you use 5,6 as reactants, or you use 7,8 as reactant. In both cases, the reaction mechanism will be SN2. We are preferring this alcohol 6 because in case of 6, the substitution will be much better, because this benzyl chloride cannot undergo elimination, which is possible in case of other alkyl halide. Okay, so here we have sulfides, and we are to carry out the retrosynthesis. So consider this molecule, and the disconnection you have to try is carbon and sulfur disconnection. Again, we are not going to break the bond between sulfur and the benzene carbon, because the carbocation will not be stable. So here, after disconnection, we have get negative charge on sulfur and positive charge on carbon. Again, next step will be to convert these into meaningful fragments. So simplest way, attach a proton to the sulfur, that's negative charge, we will get a thiol, and attach a halogen to the positive charge, we will get the benzyl chloride. So these are two units. So again, you can attach a halogen to this positively charged fragment to make it a useful entity. So we can have an alkyl halide here, right, and an OH negative here. Right, just okay, so this is okay. So when we have diols, 1,2 diols, if two groups are attached to their adjacent carbons, right? So this is one carbon number 1 to which an OH is attached, and we have carbon number 2 to which some other group is attached. So we are just imagining that both of these are OH, both of these are diols. So these are 1,2 diols. So when we have to disconnect a bond, so we are considering one OH as an X, just for differentiation purpose. So the disconnection will always result in formation of an epoxide and an X negative. Right, so you just imagine that if you have an epoxide and attacking an OH negative charge on the epoxide, will result in formation of a diol, which will be 1,2 diol. As usual, the carbon should bear a positive charge and X should bear a negative charge, and as by convention we are going to attach a halogen on this carbon, and the X will act as a nucleophile. So whenever halogen is attached to the carbon, so carbon will become deficient and X will attach, causing the addition of this group to substitute the existing halogen. So we can make of any nucleophile. It can be OH, it can be any halogen, it can be sulfur, etc. Okay, consider another example in which we have an X group which is attached to beta carbon of the carbonyl system. So easiest disconnection, we have to carry out disconnection between carbon and X. So the synthone for this case will be an alpha beta enone. So here you can see we have positive charge on this beta carbon. So for converting into useful entity, this carbon can be converted into equivalent substrate by considering it as an alpha beta unsaturated system here. So as you know, because of resonance, the beta carbon becomes positively charged, so we can have a positive charge because of resonance here. There's no need to attach a halogen here. So upon reaction of an X negative, which is a nucleophile, to this alpha beta unsaturated system, we can get our desired product like that. Okay, so now we are considering the disconnections for carboxylic acid and carboxylic acid derivatives. So whenever we have to consider disconnection of carboxylic acid derivatives, we are looking for CX bond bracket. So we have a carbon with positive charge and X that's negatively charged. So we can consider this carbon being positive by attaching any halogen, right, or any ester group. So you just need to attach something that's electronegative, which will make this carbon negative, and that group should be good at leaving, because we are to make it leave in the next steps, right? So for example, we are considering disconnection of an alcohol, right? So this example that we are using is an insect repellent, and it's also used in perfumery, right? So disconnection, yes, the carbon will have a positive charge and oxygen will have negatively charged. So converting into useful fragments, we have to attach a proton to the negative charge, so we will get an alcohol. Here, this is one of the reactants, and to this positive charge we attach a halogen, a chlorine, right? So reaction of alcohol with the benzyl chloride will yield this alcohol and ester in a useful way, right? Okay, so we are considering a few examples. For the example, so here we are using an acid derivative, and this acid derivative is an amide, right? So you have to disconnect, and for disconnection we are not considering the benzene chlorine disconnection. Instead we are going to use for carbon and nitrogen disconnection. So nitrogen will have negative charge, carbon will have positive charge, and again the convention, you have to attach a chlorine with the carbonyl carbon, so we'll get a carboxylic acid halide, and by attaching a proton to the nitrogen which is negative charge, we'll get an amine. So by reaction of this aniline with this carboxylic acid halide, we'll get the amide, which is the reactants for this retrosynthesis will be. So this is the last step of retrosynthesis. This should be the first step of synthesis. By reaction of this benzyl chloride with this alcohol, we'll get this ester, and this ester should be yielded in good yields, right? for practice. You have to predict the disconnection. These are different compounds given, and by seeing these disconnections, you have to predict how are you going to make this compounds. Okay, so far we have discussed a number of retrosynthesis in which we had to disconnect the carbon X bond, right? And we discussed different X, whether the X may be oxygen, it may be sulfur, it can be some halogen, etc. Right, so I hope that you will be able to solve the previous exercise. Now we have another example. So let's consider this example. So we have here structure, and you can see from here that we have a benzene, right, and we have a trifluoro group, trifluoromethyl group attached to the benzene, and then we have a CH2 to the benzene ring, then a CH, and here we have an NH, and then again a ethyl group. So when we have to carry out the retrosynthesis for this structure, so you may be fascinated to know that we may cleave this carbon bond between carbon of the benzene and the trifluoromethyl group, but we are not interested in here. So instead of going for this carbon-carbon disconnection, we first check the carbon-nitrogen disconnection, which may be possible, right? So here we have possibilities. Number one, we can disconnect this bond between this carbon and nitrogen. So if we cleave the bond between the ethyl group and the nitrogen, or the other way around, so we have two possibilities here, and we are going to see what will be the consequences. So firstly, consider that we have to break the bond between this ethyl group and the NH group. So if we have to disconnect that, before that we will have to carry out the FGI, right? So if we consider that next to this nitrogen is a carbonyl group, we just imagine that suppose that instead of this is ethyl, suppose this ethyl has been derived from a carbonyl group. So if we have an acetyl group attached to nitrogen, the simple disconnection will be to disconnect the nitrogen and the carbonyl group. So in this way we will get a positive charge on the carbon and negative charge on nitrogen, right? So now you can easily see that we have an acetyl group and a nitrogen group. Now we have to convert these syntones into some realizable reagents. So simply we have to attach some electronegative atom to the positively charged carbon and hydrogen to the negatively charged nitrogen. So when we do this, we get like that. So we have NH2 here and acetyl chloride here. The simple reaction of acetyl chloride with this amino group will result in formation of this amide, and you can easily see that reduction of this carbonyl group will result in formation of this ethyl group. So this is a simple disconnection, right? So if you have to carry out the synthesis, you may draw the scheme, but briefly I will just describe here that the last step of the retrosynthesis is the first step of synthesis. So here, in order to carry out synthesis, we will react this acetyl chloride with this primary amine, right? So that would result in formation of a carbon-nitrogen bond, and we will form an amide here. Then by reduction of this carbonyl of the amide, we will get this secondary amine. So this is a simple retrosynthetic approach. Alternatively, we can also break this bond between the nitrogen and this full propyl group that's attached with the benzene ring, right? So in order to carry out this disconnection, you can see, if you imagine, suppose there is a nitrogen carbon double bond here, right? So the FGI will result in formation of an imine. So if we have an imine here, so we have a double bond between carbon and nitrogen here. So the disconnection can easily be imagined. So you know that imines are formed by condensation of aldehyde or ketones with amines, right? So we have to condense this amine, ethyl amine, with this ketone, right? So condensation will result in formation of an imine. So the retrosynthesis will result in formation of the synthons, which will be a ketone and an amine. So in this way, by looking backward, by looking at the reactant, at the product, we can decide or we can predict which reactants will be required to carry out this synthesis. So it will be your assignment as well to draw all other possible retrosynthesis which will be possible for this product, right? So you may think about how you can bring an NH2 here, right? So you can think about different strategies by which you can bring an NH2 here. So, and if any other possibility exists, also you have to draw the synthesis scheme for this reaction. Okay, so we have another example. So you can see the structure. So the first step for retrosynthesis, when you have to carry out, is first you have to identify the functional groups. Right. So in the structure, we have what functional group? We have a benzene ring, and we have a hydroxy group, and then we have a nitrogen which is attached to the benzene ring, followed by carbonyl group. So we have a hydroxyl group, which is a phenol in this structure, and we have an amide functional group as well. Next important thing you have to know, if you have an aromatic based organic compound, what is the relationship of the substituents? So you have an OH, which is para to the amide group, right? So if you have to disconnect, so we have now three possible disconnections. Either we can disconnect this carbon-oxygen bond between this benzene ring and the hydroxyl group. Second possibility, we can cleave the bond between this nitrogen and the carbon of the benzene ring. Thirdly, we can disconnect the bond between the carbonyl carbon and the nitrogen. So first two options, in which we were to disconnect the bond between this carbon and oxygen, this is not feasible. Why that's not feasible? Because if we disconnect that bond, then in that case carbon will have a positive charge. So benzene carbon, the carbon of benzene ring is sp2 hybridized already, and having a positive charge on this carbon will not be stabilized, because whenever you have to create some synthone, then that synthone should be stable as well. That should be stabilized by some factor. But generating a positive charge on the benzene ring will make the system unstable, so this is not possible. So we cannot disconnect the bond between a benzene ring and the hydroxyl group. So always remember that whenever you have a substituent attached directly with the benzene ring, we cannot break the bond. Instead, we do the functional group interconversion, which is called FGI. Right? So we cannot disconnect that bond. Further, also we have the bond between carbon of the benzene ring and nitrogen. So we can also disconnect that bond as well, because if disconnected, disconnection of this bond will result positive charge on the benzene ring, which is not stable as well. So what we do, actually we disconnect the bond between nitrogen and the carbonyl of the carbonyl, because if we disconnect that one, so nitrogen will have a negative charge. So nitrogen is electronegative atom, and negative charge on nitrogen will be highly stable. So we can afford that, and then we will have a positive charge on the carbonyl carbon. Right, so we can make it convenient. So carbonyl carbon having positive charge, if you have to convert it into some realizable synthone, simple way is to attach a halogen. So we will get an acetyl chloride here by attaching a chlorine to the carbonyl carbon. So we will get an acetyl chloride, and this nitrogen with negative charge can be converted into some realizable synthone by attaching a proton to it. So the synthones can be converted into an acetyl chloride and an amine here. Right, so we have got this group. Now the next thing is that how we will disconnect further. So how can we prepare this reagent? Again, we are having two options. the first option is either to disconnect the bond between this oxygen and benzene ring, or the carbon and the nitrogen ring. Right? So if we disconnect the carbon and nitrogen, the problem will be that how we will introduce this NH2 group to the benzene ring. That will be a problem. So we must know for a reaction that how we can bring that NH2 onto the benzene ring. Similarly, if we disconnect the bond between carbon and oxygen of the hydroxyl group, then we must know a synthetic scheme by which we can introduce this group onto it. So both can be done, and we'll see which one is more feasible. Right? Just remember the basic rules for disconnection, that you have to prefer the scheme that has minimum number of steps. Right? So first we will consider the synthetic scheme, considering that if we break the bond, if we disconnect between carbon and nitrogen of the amino group. Right? So if we have to disconnect the carbon and nitrogen of the amino group, instead to break the bond, we do the functional group interconversion. Right? So here we will do the functional group interconversion. How? We know that NH2 can be obtained simply by reduction of the nitro group. Right? So we can have a nitro group, and the reduction of this nitro group will yield this amine. Right? So functional group interconversion of the NH2 will result in formation of nitro group, and we can easily introduce the nitro group simply by carrying out the nitration. So what we get a phenol. Right? So phenol has an hydroxyl group. So hydroxyl group is ortho-para-directing. So nitration in presence of nitric acid and sulfuric acid result in formation of an ortho and para isomers, which can be easily separated by means of steam distillation. Right? So in this case, so the phenol is a readily available reagent, so we don't want to disconnect it further. Right? So for conversion of this amino group, functional group interconversion of amino group into nitro, and then introducing nitro onto the phenyl ring, that will cost us 2 steps. But if consider that we have a NH2 group attached to the benzene, so we have aniline, and starting from aniline we have to introduce a hydroxyl group. So how can we do that? In order to do that, we will firstly carry out the nitration of the NH2. We will carry out the nitration of this aniline. So carrying out nitration of the aniline has its own disadvantages, as you know. So suppose we carry out the nitration of this aniline, so we will get ortho-para isomers. We will separate these ones. Then we will carry out the reduction of this nitro group into NH2. Right? And after reduction of this nitro into NH2, we will carry out diazotization. Right? So diazotization, and after diazotization we will substitute this diazonium by water or some hydroxide source. So see, in this case we have involved 4 steps into the scheme. Right? You may write down that scheme as well for your convenience. Right? So which will be better scheme? The scheme that has lesser number of steps will be better. So this scheme, in which we actually carry out the functional group interconversion of the NH2 that yields a nitro group, and nitro group can be easily brought onto the phenol by simple reaction of nitric acid in presence of some protic acid. So this is simple retrosynthetic approach. So this will be your assignment, that you have to draw the synthetic scheme for that. So I've just narrated that how will you disconnect these bonds, but you have to carry out the disconnections in written form on your own, and also you have to predict all other possible schemes which you can use to carry out this retrosynthetic approach. In this lecture, we have studied about how we can carry out the carbon-X disconnection. We have studied some general rules for carrying out retrosynthesis. We saw how we can disconnect and rationally think about the disconnection for different type of functional groups that involve carbon X disconnection. So let's review all of these concepts, and we will make use of a simple example. So here we have a molecule. So in retrosynthesis, the target molecule is your goal, is your target. This is the molecule you're trying to make, right? And what do you mean by retrosynthesis? Retrosynthesis means reverse of synthesis, right? And when you carry out the retrosynthesis, the ionic species or the charged species that are obtained, these are called synthone, right? Also, it's not always compulsory for us to break a bond. Instead, we can convert one functional group to another. So interconversion of these functional groups is called functional group interconversion, which is normally shortly abbreviated as FGI. So when we carry out a breakage of bond, when we break a bond between carbon and some other element, so this is not FGI, this is called disconnection, right? So we have a target molecule, which is the molecule we are trying to make. Retrosynthesis is actually reverse of synthesis, and retrosynthesis either involves functional group interconversion or it involves disconnection. So disconnection means actually you're going to break the bond, right? So once we break the bond, we get positive ionic species and negative ionic species. These species are not real, right? These are just imaginary species. So these are called the synthone, right? So when you have to convert these synthones into something which can be realized, right? These realized species which actually exist in nature, these are called synthetic equivalent to the synthone, right? So suppose we break a bond and we get a carbon with positive charge and nitrogen with negative charge. So these charged species, they are called synthone. They are not imaginary. But when we have to realize that how we can carry out this step, which reagents are actually to be used, we convert these synthones into something which is realistic. So this something which is realistic is called the synthetic equivalent, right? The synthetic equivalents are the actual reagents which exist. So considering all of these things, now we have a molecule, and we are going to think about how we can rationalize, how we can carry out the retrosynthesis for this molecule, right? So here we have a benzene ring, so we have to just firstly identify the functional groups present. So we have a T20 functionality which is attached directly to the benzene ring. Then we have a NH2 group which is attached to the benzene ring. Okay, so we have identified all the function groups. Next, we have to see the relationship of these function groups, because the system we are considering is an aromatic system. Right, so we can see that the relationship of these two function groups is 1,3. They are meta to each other. So next we have to think that how can we bring about the substituent at meta position. So there we have possibility that we can disconnect the bond between carbon-carbon, so carbon of the benzene ring and the carbonyl carbon. So we can disconnect that bond, or we can disconnect the bond between carbon and nitrogen. We can disconnect the bond between the carbon of the benzene ring and the nitrogen. So if we disconnect that bond, so benzene will have a positive charge which is not preferred, which is not stable. Right? We cannot have a positive charge on benzene ring. Similarly, we cannot have a negative charge on benzene ring as well. So else we can try about something else. But here, since we are discussing about the carbon X disconnection, so we will discuss about the bond between carbon and the nitrogen. So again, instead of breaking the bond between carbon and nitrogen, what we do is that we imagine that we carry out the FGI. Right? So we can simply imagine the FGI. So how can we get the FGI? We know that NH2 can be easily obtained by reduction of a nitro group. So FGI of this molecule will yield a nitro group and instead of the NH2 group, right? So we have got a nitro group here, and now you know that this nitro group is meta to this carbonyl group, right? The carbonyl is meta-directing, so it's easier to bring a nitro group there. So how we'll rationalize further? We can say that starting from acetophenone, we carry out the nitration of the acetophenone. So acetophenone is a readily available reagent, so we don't need to synthesize it further, right? So starting from the acetophenone, we will carry out the nitration of the acetophenone, and nitroacetophenone, which is at meta position, it can be reduced to yield an NH2 group. Right? So in this way, we can step by step rationalize how we can synthesize a molecule by looking backward. So we just critically analyze the product. We can imagine and we can predict that which reagents will be necessary to carry out this synthesis. I hope you have understood the lecture about one group carbon acid X disconnections. Thank you.
And thank you.